Login accepted.
All right, that must be my cue to start. So good morning, everyone. Welcome to Granularity and Coupling in Microservice Architectures. My most recent book was a book that I wrote with Mark Richards called Fundamentals of Software Architecture. And when we wrote that book, we were trying to really distill, what it takes to, what is the minimum viable product if you were to be a software architect. But we kept bumping into problems as we wrote that book that were just too difficult to deal with in a fundamentals book. So we set those aside in this pile that we grew to call the hard parts pile, the hard parts of software architecture. Well, when we finished that book a little over a year ago, we approached that pile that we had gathered up and started sifting through it to see what is making these problems so difficult. And that, of course, led to this book, which comes out in about a month, which is now in copy editing at O'Reilly, Software Architecture, the hard parts. It's all the difficult parts of software architecture. And one of the things that we figured out as we were looking through these difficult problems is that they seem to sort of coalesce or revolve around two major features in microservice architectures. And that's what I'm going to talk about this morning: granularity and communication in microservices. This is something that we discovered as part of, we're both consultants professionally, and this is one of the two things that teams that are doing microservices seem to struggle with the most. What is the appropriate size for my microservice? Because one of the common things you do when you start doing microservices is boil everything down to these tiny little things. And then, well, to get them to do useful work, you have to get them to start chatting with one another and do transactions. And now everything is slow and complicated, and you've built a distributed ball of mud, which is not what you wanted to do. And so let's talk about these two forces in software architecture. And we will start with granularity. One of the things that we wanted to do is do a little bit more analysis around coupling in software architecture, which is fundamentally what this book is about. And this set of ideas actually started back in 2017 in this book, Building Evolutionary Architectures, which was my soon-to-be 3 books ago. And one of the things we wanted to do in that book was, can you assess general architectural styles to see how evolvable they are? Which is another way of saying, is there some inherent characteristic of an architectural style that makes some more evolvable than others? And we looked for a lot of concrete measures for that and couldn't really find any that we liked, and so we created one of our own, which we called an architectural quantum. And we borrowed the quantum term for the same reason the physicists borrowed it, is an unbreakable thing. And so in the evolutionary architecture world, an architecture quantum is an independently deployable component with high functional cohesion and synchronous dynamic coupling. And that was sufficient for figuring out evolvability. But as we started digging into the hard parts world, we realized that we needed to go deeper in this definition. And so here is the more modern definition that we're using to analyze architectures. It's still an independently deployable artifact with high functional cohesion. So you can almost think of this as a bounded context from domain-driven design. But we didn't want to use the term bounded context because, well, that already has a distinct meaning in domain-driven design. And while this is like that, it's not that. This is really a measure of how things are coupled together and how operational they are. And that's the first part of this, independently deployable artifact with high functional cohesion. That really describes the ideal in something like microservices. But we also went a little bit deeper and used some material from a book written in 1993 called What Every Developer Should Know About Object-Oriented Design. And one of the things that author did that was very clever was separate coupling in software architecture into 2 categories: static coupling and dynamic coupling. And that's reflected in our definition here. Static coupling is how things are wired together within an architecture. These are all the dependencies within an architecture. And this is how we think about this in the Hard Parts book. It's how static dependencies resolve within the architecture. So that includes things like the operating system, frameworks or libraries that you depend on, any integration points that you have in architecture. You can think of this as how a particular service is wired. And so to be able to bootstrap this service, what has to be up and running and functional, that's part of the static coupling of that architecture quantum. And this is a useful measure all by itself. In fact, several of our clients are going through this static quantum mapping exercise because this is the answer to, if I change this thing, what else might break because I changed this thing? That's the static coupling within an architecture, things that are coupled together, and that's a useful thing to know within architecture. The other part of this is how things call one another. So if a service bootstraps itself, it's running, but then to call another one has all sorts of other decision impacts. And so we actually think about those two things separately. So let's talk about the static part of this and get to this idea of granularity in microservices. This is one of the most common questions you get, particularly for teams that are new to microservices. What is the right level of granularity for my service? And it turns out that there are two opposing forces at work here. One that we call disintegrators. These are forces that encourage you to break things down into smaller pieces. And this is unfortunately the only force most developers use. And you end up with services that are way too small, that are really difficult to deal with for lots of different reasons. The other force, the opposing force, are integrators, things that encourage you to bundle things back together when they've gotten too small. And let's talk about these. There are 5 disintegrators and 3 integrators. So let's go through each of these. The first of these disintegrators is service functionality. And this is really about looking at your problem domain and doing a domain analysis to see how things should be broken down. So maybe now you have a notification service that has SMS and email and postal letters, and you decide, well, based on domain functionality, this should really be decomposed into 3 services: an SMS service, an email service, and a letter service. And so that's this idea of service functionality as a driver for breaking things down. And if you only follow domain-driven design as a way to do your architecture, then you end up with a good design, but maybe not a good architecture, because this may create all sorts of issues in terms of coordination or data or transactionality or reliability or a bunch of other things. So here's another question. Should I consider breaking apart this service based on service functionality? And this is a customer with profile and preferences and comments. Maybe this should be broken down into 3 different services as well based on the functionality of this particular problem domain. The second one of these disintegrators is volatility or rate of change within a part of your system or particularly within your domain. This is about, so if I look at my notification service and I realize that the SMS and email code rarely ever changes, but the postal letter, because of regulations in different states and different countries about wording, that has to change all the time as an artifact of the business that we're in. And so based on volatility, I might say, well, the better separation of these things are the things that hardly ever change and the things that change all the time. Now, this is a great example of something I'm going to talk about tomorrow morning in my keynote, which is about evangelism in the architecture world. Because you will talk to a small cult of architects right now who will tell you that volatility-based decomposition is the only thing you should ever think about in architecture ever, because that is my new religion, volatility-based decomposition. But that never works when universally applied. In fact, you can never give broad general advice like that in software architecture, because what happens is someone works in a particular field and volatility becomes a really important driver and they start thinking, well, that's true for everything, but almost nothing is true for everything in software architecture. But it is one of the really important drivers. Look at how volatile things are, because rate of change is a nice way to separate things. The third of these is scalability and throughput specifically, but this whole family of what we call operational non-functional requirements really belongs in this category. These are things like scalability, performance, elasticity, reliability, availability, all these things that overlap with operations and DevOps, etc. So for example, let's say that I have my notification service with text, email, and postal letter. And here is my scale that I have to be able to support for each of these. 220,000 a minute for text, 500 a minute for email, and 1 a minute for postal letter. Well, there's an obvious separation there that we can make to separate those things based on scalability. And in fact, scalability is one of the big drivers that force you to break up your monolith into distributed services, because you can't scale the whole monolith, and so you need to break it down in smaller pieces. That's obviously one of these disintegrators, any kind of operational perspective like that. This is another one of those that gets a special mention: availability, reliability, fault tolerance, and that whole family of availability parts of architecture. Let's say that for various reasons that email is really fragile as a service within my ecosystem. And of course, if it's part of a larger notification service, then if email goes down, it takes the whole thing down, which is obviously not good. This is one of the problems with monolithic things in architecture. Now, if I separate this out based on reliability or availability, then if one service goes down, it doesn't necessarily affect the other services. And now you can start using things like asynchronous communication and message queues to wait for it to come back up and build higher levels of reliability at the architecture level. And then finally, another that gets a special call out because it's a special consideration in most places: security and building secure systems as a disintegrator. So if I have a profile service that has profile info but also has some sort of sensitive information like credit card information, then I may obviously want to split these apart so that I can have much more hardened security on the one that has more dangerous information in it, or even personalized identification, PII data in it. So these are all examples of disintegrators, and there may actually be more of these within your organization, but this is a pretty good list of generic kind of disintegrators. And as I said before, this is all most developers apply, because this is, it's kind of fun to go through and refactor and carve things up into small pieces, but very often you find out that you carve things up too small. So let's talk about integrators. When should you consider bundling things back together? Because one of the important things to remember about microservices, and this is an observation made by Martin Fowler and James Lewis in the article that popularized it, the word microservice is a name, it's not a description. It's not a commandment to make things as small as possible, but rather this idea of building things around bounded context and the principles in domain-driven design. So let's talk about a few of these integrators. There are 3 of them. One of them is database transactions and transactionality. This is one of the common places where your business people or your problem domain is telling you what needs to be together and what needs to be apart. Because one of the things you want to try to avoid in microservice architectures are distributed architectures between services. For example, if I need to register a new customer and I need security info to be transactional there, this is generally considered a no-no in microservice architectures. It's not because it's not possible, and it's not because they're not patterns that are designed to do this. It's just really hard to get correct. And it also tangles up a lot of other stuff that we'll talk about as we talk about the communication side of coupling. This, it turns out, transactionality is one of the primal forces in communication in microservices, and so it has to have some special considerations. And so in this case, rather than break these two things apart, why not bundle them together into the same service? Now the transactional boundary is inside the service boundary. I'm no longer doing distributed transactions, and things will probably have a higher performance in my architecture because I'm not doing as much at the architecture level. I'm doing more in process, which tends to get better performance. The second one of these common integrators are data dependencies. This is one of the revelations that Mark and I had after our fundamentals book, as we realized that increasingly data is becoming an important consideration for software architects, more so than it was a few years ago and increasingly now. A lot of this is because of the nature of microservices. In fact, Mark and I both have been doing architecture for quite a long time, and we built a lot of distributed systems back many years ago in terrible technologies like Corba and DCOM and a bunch of other terrible acronyms like that. But decisions in microservices around things like granularity are much trickier than in those other distributed architectures, even if a lot of the other things are the same. And we were trying to figure out why that is. And it's because that data has moved into our decision space. Because most of the distributed architectures you built with COM and Corba and DCOM, et cetera, still talk to a big relational database and let it manage most of the transactionality. But when you make data and transactionality part of the service boundary, that means things like transactions become part of the architect's concern, and things like data dependencies become much more of an architectural concern. And let me describe what I mean by that. That's why, by the way, we added two co-authors to the Software Architecture of the Hard Parts book, whose names you may recognize, Pramod Sedalge, who wrote the Refactoring Databases book, and Zhamak Dahagani, who's writing the Data Mesh book, Operational and Analytical Data, because increasingly data is a really important factor in software architecture. So let's say that you have this service component with these three chunks of functionality in it, but they're also mapped to some tables in a database somewhere. And so my instinct as a developer says, well, I should break these three components up into three separate services, right? Okay, that makes perfect sense. But now I've got to map the data dependencies back. Okay, well, it looks like function A uses tables 1, 2, 4, and 6. B writes to table 3 and reads from table 5, and C writes to table 5 and reads from table 3. Okay, well, this is just a puzzle game. We can slide the tiles around and match things up, so we can move those over to A. That makes perfect sense. And we can move 3 over to B, and that number 5 over to C, and we're all done. Oh, wait, there's some leftover arrows there. Okay, well, we could do that. You're really not supposed to do this in the microservices world, because what you're doing, if you do that, is expose the schema details of this other service to service B, which means these are now coupled together in the worst possible way, because as soon as you change the schema in C, it's going to break B or cause you to have to do something with it. This is exactly the kind of coupling we're trying to avoid in microservices, this really low-level implementation kind of coupling. And of course, we'd have to do the same thing here, which obviously doesn't make anything prettier. We could do communication, orchestration, or choreography. We'll talk about that in a second. But then the question becomes, how much do you need this information? These are just reads, but how often are you reading this stuff across those tables? This is the secret to why a lot of microservice architectures have real performance issues. Because they do data isolation correctly, but now they're doing all this chatter back and forth using HTTP or message queues or something, and that's much slower than doing a direct database lookup or an internal in-process call somewhere. And so it may make sense in this world to say, you know what? Unless there's a strong driver, another one of those disintegrators, in fact, that's forcing me to keep B and C apart, let's just bundle them back together. One of the things that may force me to keep them apart is they do legitimately need different levels of scalability or elasticity or something like that. But if it's just the fact that they have 3 different domains or 2 different domain behaviors and you have all these coupling points you need to resolve, this is a much simpler way to model that architecture. And then finally, the third of these is one that I've already alluded to, workflow and choreography. You build your nice, beautiful microservice architecture. Everything is a really nice bounded context with good isolation and low coupling. And then you start trying to get it to do useful work. And you discover that all these things are talking to all the other ones all the time. And then one of them dies. And guess what? They all die. So congratulations, you've built a distributed ball of mud, which is more sophisticated than a monolithic ball of mud and much more difficult to build, but there it is. The other problem, of course, too, is that, okay, I need to make a request. Okay, this one has to hop to this one, 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 and you eventually get a request back. But this is why scalability is really good in microservices, but performance sometimes needs tuning because of exactly this issue of too many hops. And of course, you have liability and data consistency issues as well, because if you have all these communications and you get a timeout, then you've got to either write around that or do something about that. And so in a lot of cases, rather than do elaborate workflow and choreography, particularly if they need to be transactional as well, then you're better off, again, just bundling those into a single service. Even in the article that sort of introduced microservices and that concept to the world by Martin Fowler and James Lewis, several of their services are fairly large because, remember, the goal is to capture a bounded context, not some arbitrary smallness within your architecture. And unless there's some other compelling disintegrator that gets you to disintegrate that, then that's probably a good thing to think about. And it's a good idea to apply both of these as you start thinking about designing your architecture. The other thing that's important about this is to iterate on your design. No matter how good an architect you are, no matter how many systems you've dealt with, it's almost impossible to walk into a place and nail that granularity question right out of the gate. And so what you need to do is iterate and then come up with disintegrate, integrate, etc., and iterate toward a good combination of what the right level of granularity is, taking a lot of these things into account, including the communication stuff that I'm about to talk about here in just a second. These are all good bits of advice as a way of getting to the right level of architecture. Because one of the tricky things about architecture that we've realized, Mark has a great phrase for this: architecture is the stuff you can't Google. Because when you're a developer, one of the skills that you build is being able to Google for solutions to things and finding solutions like, hey, that's great. But when you get into architecture, first of all, think about the architecture of where you are now. It's a combination of things that we like and things we don't like and legacy things that we hate and some stuff that we have to deal with and some packaged software and a whole bunch of magical snowflake full of unique things. What are the chances anyone else in the world has your same set of tools and frameworks and et cetera? And even if they have they encountered the problem that you're just trying to solve? And did they have enough time to write a nice Medium post about how they solved that problem? Chances are probably not. And so this is why it's important to take generic advice, but then immediately try to apply it to your unique snowflake of an architecture and iterate on your design, because there are no silver bullets, particularly when you don't even know what the werewolf looks like. And so that's granularity. Let's talk about communication. We realize that communication in distributed architectures, and this is distributed architectures broadly, but microservices specifically, really boils down to 3 dimensions But our recent insight is that these are conjoined dimensions. Let me show you what I mean by that. The first of these dimensions is communication. Is this a synchronous or asynchronous call in architecture? The second of these is consistency. Is it atomic or some level of eventual consistency? I'll talk about that in turn in a second. And then the third dimension is coordination. Is this choreographed or is it orchestrated? So let's talk about these three forces individually, and then we'll tie them all together into a conjoined three-dimensional space. So let's first talk about communication. Synchronous versus asynchronous. This has a big impact on decisions in distributed architectures because it has an impact on timing and performance and reliability and availability and a bunch of other things. So one of the things that we're trying to do in the Architecture of the Hard Parts book is use the simplest definitions we can for these core architectural concepts, because you can start pulling at these threads and be there forever. And so here's our simple definition for when we're talking about synchronous communication. A synchronous call is when a caller waits or blocks for a response, and an asynchronous call is when a caller responds asynchronously. So sends a message and then immediately returns back to work and then gets notified that that answer has arrived. And so obviously there's a huge difference in timing here, because for a synchronous call, let's say it takes 50 milliseconds to make a call, it takes 1700 milliseconds for it to service that call, and another 50 milliseconds to return that call. That's 1700 milliseconds, 1800 milliseconds round trip, 1700 plus 100, 1700 milliseconds round trip for that synchronous call between those two services. That means that the yellow service here can't do anything else while it's waiting for that synchronous call to come back, which of course has implications in terms of performance. Versus asynchronous calls, where a 25 millisecond post to a message queue and then an acknowledgement, now the yellow service can go on and do other things, handle other requests, and then get notified when that request has completed by that green service. And of course, there are lots of different ways to implement that, but that's the fundamentals of synchronous versus asynchronous. The reason this is so important when you're talking about communications in distributed architectures, and I promise this was accidental, but when you make a synchronous call between two services, you create dynamic quantum entanglement between those two services for the length of that call. Because you can't have these two services operating at vastly different scales if they're making synchronous calls between one another. Because if the yellow one is operating at 10 times the scale, then you're going to get all kinds of reliability and timeouts and a bunch of other issues in this architecture. And so synchronous calls in an architecture temporarily tangle things up around their operational architecture characteristics. And then when that call goes away, they can be independent again, but synchronous calls create these kind of entanglements. So for example, if you have two services that make a synchronous call between each other, then one has to wait for that call to resolve. Asynchronous calls give you a little more flexibility. This is not a complete get out of jail free, but it gives you more flexibility, because if the service on the left here, bulk transaction, is operating at higher elasticity or scale than the routing service, but if it's a burst of new requests, then that message queue gives you a buffer to stack up those requests and then bleed them out to routing over time, so that you don't get reliability and other issues in architecture. And so asynchronicity in architecture allows you to build more reliable connections between things because you're not tied to those synchronous calls. And so for synchronous calls, the trade-offs here: you can have a performance impact on highly interactive systems. It creates these dynamic quantum entanglements between services, and it creates limitations in distributed architectures. But the nice thing, because of course everything in software architecture is a trade-off, it's much easier to model transactional behavior if you're doing synchronous calls, because if I need to wait to find out if I've got that seat confirmed or not, and then it can come back. I don't have to wait, so that's much easier to model that kind of behavior. It mimics non-distributed method calls, which makes it easier to think about, which makes it a lot easier to implement. Asynchronous calls are a lot more complicated to build and debug because now you have to deal with deadlocks and race conditions and all sorts of nasty beasts in distributed architectures. It makes transactional behavior more difficult, although not impossible. So eventual consistency is definitely preferred there. And it makes things like error handling more complex. Not impossible, but this adds to that complexity. But on the good side, it creates really highly decoupled systems, decoupled not only from a contract standpoint, but an operational, architectural characteristic standpoint, different levels of scale or elasticity, for example. This is a really common performance tuning technique in microservice architectures because once you've built services that are too fine-grained, you can use asynchronously to make it look like things are moving faster by not waiting so much for things to respond. And of course, this gives you a much higher performance and scale. So that's the first decision you have to make is synchronous versus asynchronous communication. The second decision you have to make is consistency. Atomic versus some level of eventual consistency. And I'm not going to talk at all about this here because this subject has been beat to death in the architecture world. You can find out lots of stuff about eventual consistency in lots of other places. When we talk about atomic here, we're not talking about an ACID transaction because you can't do an ACID transaction in a distributed architecture because you can't get all four of the A, C, I, and D. But we are talking about atomic, which is a behavioral architectural thing, which is if I make a call to something, I want all of the things to be updated or not at all. So that's what we're calling atomic. And so that's atomic versus some level of eventual consistency. And there are lots of different variations of eventual consistency. But this is the second thing you have to think about in terms of communication in distributed architectures. The third is what kind of coordination you're using. And this also depends on how complex your workflow is. And let me describe what we mean by coordination and the difference between choreography and orchestration in microservices architectures. So let's do choreography first, which is, of course, inspired by this idea of dance partners with no central coordination. And choreography is apt here because there is a choreographer who comes up with the dance steps, but as they're dancing, there's no one there specifically guiding them, typically like a conductor would an orchestra. And so for choreography, let's say that my request here is, I need a wish list for customer 123. Well, I have a wish list service which has almost all the information I need, but is missing the customer name. I have the customer ID, but I don't have their name because the name is part of the profile service. And so in choreography, the wish list service is knowledgeable enough about where to get information that it can reach over to the profile service, get the name, and then return this back to my request. So this is choreography using one of these as the entry point and then letting it find the other information that it needs. Versus orchestration. Here, I want to get all the data for customer 123. And there's no obvious choreography entry point because these are all discrete parts of data about a particular customer. And so I can build an orchestration service here to manage that for me. And the orchestration service will manage contacting each of these, looking after errors and other sorts of issues, and then eventually returning the aggregated or combined or some combined approach back to my consumer. Now, this is a very common feature that's been around in architecture for a long time. One of the big differences in microservices, of course, is that you do orchestration per workflow. You never have a big, giant global orchestrator like an enterprise service bus. So this is meant to be very tightly bound to whatever workflow it's doing, but it's there to facilitate not only this coordination, but also a bunch of other useful things, which I'll get to in just right now. So having an orchestrator here allows you to do some really useful things. First of all, it gives you a place to put error handling logic and other sorts of timing, and so other sorts of workflow complexities can go here. It can also be either point-to-point or multicast, so you can use things like topics and event queues here so that you get durability based on the implementation you're using to implement your communication medium in that architecture. One of the key things here is error handling. When you look at a workflow in a distributed architecture, it's not just the happy path, but it's also the error conditions, boundary conditions, and other things that you're going to have to model to be successful for that system. And having an orchestrator there makes things a lot easier, because if I'm trying to make this call and one of those services is not available, well, now the orchestrator can decide, should I retry, should I give it a little bit and try again, should I send back incomplete information, should I return an overall error message? I have a good place to make that programmatic decision if I have an orchestrator. If I don't have an orchestrator, that decision's got to be made, but that logic has got to be dispersed across all of those choreographed services, making all of those a lot more complicated, because now they have to deal with errors of workflows that they are a part of. And then finally, this gives you a good place for contract ownership, because it may be that just like musical chords, each of these services may be producing a particular tone, but what the caller really needs is a complete chord. And so this gives you a way to do aggregations or combine things or do additional business logic. This also gives you a good place to store state. So if I need to query the state of a workflow, then having an orchestration service there where I have queryable state is a really nice thing. Now, of course, putting state in the orchestrator may make it less scalable, so there's another trade-off decision you have to make, but it makes things a lot more convenient, particularly if you have really complex workflows. And there's a pretty strong correlation to complex workflow and the need to have an orchestrator there to manage those things for you. So those are the three forces, at least the three forces, that you have to think about when you're making decisions in a distributed architecture. And our recent revelation that we've been writing about is realizing that too many architects are trying to make these decisions in isolation from one another, and you can't. Because if you switch from synchronous to asynchronous, it greatly impacts your consistency. Because if you're trying to do atomic and asynchronous, now your job just got way more difficult than it was before. You just changed one factor, but now everything is more complicated. And so what we realized is this is a conjoined three-dimensional space. And each one of the possibilities here, so there are 8 different binary possibilities here. If you know a little bit about combinations or permutations, that means 2 to the third, which means there are 8 possible combinations of these binary choices that you can make. And of course, even between those, because of eventual consistency, there's a whole range of things there. And so what we did in the Architecture of the Hard Parts book is actually analyze all 8 possible combinations that come from tweaking each of these values, and created all of these. These are all versions of a Saga, because this is the Saga pattern transactionally in architecture, but they all have their types of Sagas. And so let me talk about a few of these here. One of these, the first of these, is what we call the epic Saga. This is what most people think about when they think about something like a Saga. And so this is, and you'll notice we have a superscript after each of these that indicates its communication, consistency, and coordination values. And so this is synchronous, atomic, and orchestrated. That's what an epic Saga is. So you don't have to memorize the little titles. And that's where this is right here at the origin of our three-dimensional space here. Notice that this is synchronous, atomic, and orchestrated, which is exactly what you have in a non-distributed architecture. And so one of the things that makes us think that we may be onto something here is if you move the little dot directly over the origin, you're no longer in a distributed architecture, you're in a monolith, which is in fact synchronous, atomic, and orchestrated. And this epic Saga tries to model that behavior as much as possible. So for each one of these patterns, we created what we called an isomorphic diagram that illustrates the issue with that architecture. So this is isomorphic, meaning there's no actual domain behavior for any of these services. This is what happens if three services need to communicate with an orchestrator. And so in the case of an epic saga, it's synchronous communication, so solid arrows, atomic consistency, which means we want the entire workflow to complete or not at all. Which means the orchestrator has a fair amount of work to do, because in the happy path, you call the three services, everything's good, you return, everything is great. But what happens if the second service fails? The orchestrator then has to issue compensating updates to the first and third service to say, please undo what you did before to get back to that completely atomic state that we had before. So that's the isomorphic diagram that describes that architecture. And for each one of these, we also created this chart of ratings. The coupling in this architecture is very, very high, because of those three forces, you look at which one of them increases coupling and which one decreases coupling. Synchronicity increases coupling, orchestration increases coupling, and what's the third one? Atomic increases coupling. So those are all three of the high coupling things together. The complexity is fairly low here because it's fairly easy to understand this pattern, although it's fairly tricky to implement. Responsiveness and availability are really low here, because in that distributed architecture, you've got to wait before you can complete that entire workflow for all those things to finish or to get rolled back, and so that's going to impact responsiveness and availability, and also scalability, because that orchestrator becomes a bottleneck. What happens if you move the ball? And so here what we've done, we're still synchronous and atomic, but we move to choreography instead. So here's the isomorphic diagram for what we call the phone tag saga. Here we don't have a central orchestrator. And so the request comes into the first service, which changes it on to the next one, which changes it on to the next one. What happens if the third one dies as part of its request? Well, now we need to daisy chain back in the opposite direction to tell them all to undo what we wanted, because notice the blue dotted barrier there. The whole thing is trying to be atomic. So it is possible to model this, but now you're getting much more complexity in your domain services. So that workflow that you've got defined, that complexity has to go somewhere. It's either in an orchestrator or spread out amongst those domain services, which is why, as you can see, complex error conditions becomes more and more difficult if you have to spread that logic out and that knowledge out and coupling across all three of those domain services. So here the coupling is still high because we still have atomic consistency, and we've only really notched down one of the coupling characteristics, which was choreography. The complexity is high here because now you've got to spread all that complexity across those services. Responsiveness and availability are low, and so are scale, because you're trying to tie everything together with that transactions. So I'm just going to talk about a couple more of these. I won't do all of them. These are not all patterns. Some of these are anti-patterns. And this is one that we call the horror story, which is asynchronous communication, atomic coordination, and choreography. This is the most difficult combination to achieve in an architecture like this. But it's worth naming all of these things, even the anti-patterns, because all 8 of them are legit in at least some scenario, but some of them are easy to stumble into. I was recently working on a project, and I was asked for advice on their microservice architecture, and they brought me this as their solution. And I said, that's the worst possible combination. And their answer was, oh, but no, it's a Saga. There's a pattern for that. Oh, there's a pattern for it. Well, that's a solved problem then. We can go to sleep and rest easy now. Just because there's a pattern for it doesn't mean that actually applying that pattern is going to be, any way appealing or fun or productive or possible. etc. So what a horror story tries to get you to do is have atomic consistency, but with asynchronous communication and choreography. No orchestrator to manage all this stuff. And so now each domain service has to be smart enough to handle those compensating rollback situations. But now what happens when, okay, the first request comes in, and so now I'm waiting to resolve this workflow, and now another request comes in because it's asynchronous. So now I've got to start stacking up the pending requests. So now what happens when another request comes in that is contingent upon the outcome of one of these that I've got stacked up, and now your head explodes. So it is possible to implement this, and this would give you incredible scale, but not very good from an implementation standpoint, and the most complex of all of these to try to spread all that logic around across those services. So definitely not recommended. So understanding the coupling in microservice architectures really comes down to granularity and communication. And what's interesting about communication is that what we did was look at the forces that were in play. And in fact, the way that we built all those charts is we were using the simplest possible definition of coupling, which is this artifact is coupled to that other artifact if that other artifact changes, it might force this to change, then they are coupled to one another. That's the simplest definition of coupling that you can come up with. So we looked at, in a microservices architecture, synchronous versus asynchronous. If I change that binary, what else does that impact? And so we started building a list of those things. Okay, consistency. If you change from atomic to eventual, does that change orchestration versus choreography? Yes, it changes that decision. That's how we arrived at this multidimensional space, which is not to say that you stop there. This is just the first bit of it, because there may be other concerns within your architecture. Other integrators or disintegrators like security. So then you may want to take that three-dimensional space and add security to it and say, okay, if I improve security, what does that change in synchronous versus asynchronous? Easier or harder? How does that impact things like performance and scalability? This is really the essence of how you do trade-off analysis in modern distributed architectures. This goes back to what I said earlier. Nobody has already gone and researched your architecture and come up with the perfect solutions to your problems and written it down anywhere. And nobody will except you. But what you have to do is figure out a way to analyze the architecture you have. And one way to do that is to analyze how things are coupled to one another and how changes to one affects the other. And this goes back to everything in software architecture is a trade-off. And the more you can hone that skill of developing trade-off analysis, the better off you are. In fact, you'll notice that the subtitle of our book is Modern Trade-off Analysis for Distributed Architectures. So we walk through, as our generic case study, this communication stuff generically in microservice architectures. But the last chapter, we actually talk about building these kind of matrices and how to do this kind of trade-off analysis, because that's really your only hope, because unfortunately nobody else has already solved that problem for you. That's all I have for this class. Thank you very much for coming. Hope you enjoyed it, and I hope to see you tomorrow morning at the keynote. Thank you. Thanks.